So I start here with a small module, which I call the TCP/IP architecture, which is very superficial. So sometimes it's the kind of things that some people don't like. But we need it. We need to understand the global picture a bit before diving into the different topics. So don't be misimpressed by what we see in this first set of slides. It is by nature a bit superficial, but it will save you a lot of time. It corresponds to chapter 2 of the textbook. The objective is to understand primarily terminology and what is called a layered model. So TCP/IP is an architecture for computers to communicate, or for devices, electronic equipment to communicate with each other. And it's based on a layered architecture. So layered architecture, why do we have a layered architecture? There are different, it's a philosophical statement. We can observe that it is in this way, but the main reason is the same reason why you do modules when you write a big piece of software. If you're a bad programmer, you will write a long single class with a single method, but probably that's not a good way to do things. So you want to have a software that is modular, that is built in small pieces with well-defined interfaces. This is all that layers is about. Now, why we call them layers rather than modules or packages or interfaces is that by nature of communication, things go together. It's not one layer alone. It's not an application layer talking alone, but an application layer talks to another application layer. Communication is about that. So you need at least two for communication. This is why they are called layers. Also, perhaps because we classically put them one above the other. In TCP/IP, there are 5 layers that, as you will see, correspond to very different type of skills, jobs, technologies. In other books, you will sometimes read that there are 7 layers. Sometimes people find 9, whatever. I think everybody in TCP/IP today would agree that there are 5. Like any classification of things, there is some arbitrariness in it. But this is what I'm giving here is the most commonly accepted. The physical layer is about moving information over physical medium. Even though we like to be in the logical world, at the end of the day, something has to be physical. So the physical layer is about being able to send the signals over wires, copper wires, optical fiber, wireless waves, or even acoustic waves for submarine communication. So this is typically close to physics, to electronics, and this is perhaps something done in a different course in communication systems. For example, you have a course on communication, the physical communication layer, given by Professor Rimoldi. Then we have something else which I call interconnection. Interconnection has to do with now organization, so it's not physics. It is how can we have billions of devices be entangled and communicate together. Today there are billions of hosts on the internet. How can we make a system that has billions of hosts? So we need principles. We need to organize things in a certain way. We cannot simply pool telephone wires between every system and every system. So this is what it is about. It has 2 parts, the network and MAC layer. I'll mention them, we'll study them in detail a bit later. And then there is, so this is the focus of this course. This is how we build networks. Then there is also another part which is more about software purely, which is split itself into 2 parts. The application layer is what all of this is all about. We want to do this to have access to the web, for example. The web is one application. There are several others, email, etc. Smart grid control applications. Those are all different applications that all the system is about. We will not talk much about the application layer here. This is more the topic of courses like information systems or distributed systems. Although, of course, we will do all the necessary steps to understand basic applications. And in Lab 3, you will code your own applications, which will be small, which will be exercising all those layers. And then the transport layer is also part of the software that we do when we write an application. But the transport layer is typically the software that's provided to you by the operating system. So when you write an application, you don't use natively the network, but you use an intermediate step, which is called the transport layer, which we will discuss in great detail. This is also the focus of this course. So the focus of this course is the 3 layers in the middle, except the physical, except the application. So here is a quick overview of an application layer. If we think of the application layer, this is the image we have. When I click on a web page, I am in a terminal, a web browser, a smartphone, that sends a signal, a message, to a web server. And the view that we have at the application layer is just this. There are 2 systems only. This is what we call the layered view. When we are at one layer, we can forget about the system below. And what we see is I am accessing a web server that is accessible through perhaps a name, perhaps an IP address. I'll discover that. And then you send some messages, which in that case consists in asking for a page, which you get back. The transport layer, as I mentioned, is provided typically by the operating system. Unix, Windows, they all do the same. And the goal is to providing a programming interface for using the network. Why do we need that? Well, we need it to be able essentially to provide what we call a reliable service. The reliable service means, as we will see a bit later, when we send data over the internet, it is split into pieces called packets, and some of them can get lost. If some of them can get lost, then we need to repeat them, but we need to detect which ones are lost and repeat only the ones that are lost. There are many other functions done in TCP. We will discuss them in due time, but that's the main distinctive feature of TCP. It provides a reliable service. In fact, it provides a bit more. The design of TCP was intentionally such that it makes using the internet the same as using a file, using a binary file with whatever programming language. When you use a file, what do? You open the file, and then you write bytes into the file, or you read bytes from the file. This is what TCP does. Instead of opening a file, you open a connection to a remote party, and then sending data is writing into the interface provided by TCP, and receiving data is reading. And it's exactly, literally, the same interface as from a file. This is what TCP provides. It provides what now, if we go technically, it means it provides sequence guarantee. Sequence guarantee means if I write into a file a block of 1 million bytes, they will be written by the operating system in exactly the order that I've written them into the file. TCP will do the same thing. If I send using TCP 1 million bytes to another computer, it is guaranteed that the other computer will receive the 1 million bytes in exactly the order I've sent them. This seems trivial. Why would anything else happen? Well, in fact, it may happen because the internet is packet-oriented. If these 1 million bytes fits in 1,000 packets, it may be that the 1,000 packets do not all arrive in the same order, which is what the network natively provides. So TCP adds this sequence guarantee on top. If we don't need all the bells and whistles that TCP provides, we can use UDP. We will see that TCP has a cost. Before being able to use TCP, we need to do a bit of work. If we are simply sending one little message, like we're doing, for example, when we query a DNS server for the IP address that corresponds to a name, that's a very short piece of information. Typically, we don't use TCP. Instead, we send a small message once, and doing that is done over UDP. UDP is essentially nothing other than adding UDP ports that we will discuss in more detail a bit later. The socket is the interface that you use when you use the transport layer. If you use natively the transport layer, you're using the socket interface. Now, very often as a programmer, you don't use natively the socket interface. You use intermediate middleware that hides some of the complexity. What we will do in the lab, in the programming lab, will be to use exactly the socket, because that will allow us to really understand the network. Now I mentioned what a network layer is doing. Well, a network layer is solving the problem illustrated here. How do we interconnect billions of systems together without having billions to the square of wires? So how can we do it? Let's go a bit through history. Historically, what was done when I was a student, we had one computer in the campus and we had email, but when we would send email, we would send a message to the computer. We were working on the computer from a terminal, not from a PC. We just a keyboard and a display, and everything was done on the computer. The display was just echoing what the computer was doing. And if we would send a mail, then the mail would be sent to another computer that would forward it to another computer, etc., until it finds its way to the destination campus, where the destination could read it and get the message. This was called store and forward, and until the 90s, most email was done in that way. Store and forward means I have a piece of information, an email or a video file, and then I have a network of computers that pass the message from one to the next until they reach the destination. This is not how the internet works. The internet uses packet switching. Why does it use packet switching? Well, we'll see a second. In the internet, we don't send an entire piece of information except if it's very small. If it fits within IP packet, a packet is, roughly speaking, 1,000 bytes up to 1,500 in some cases, sometimes even more. But let's say, roughly speaking, 1,000 bytes. And anything bigger is split into smaller packets. And each of the smaller packets behaves like a postcard. It is routed through the internet until it reaches the final destination. So if I take a current view of what would happen when we send a mail today, we still have a mail server, but we're connected to the mail server by a network of routers. The routers are those cheese boxes here. And this mail was made of 3 packets. When the mail server decides to send it to another mail server, it will break it in 3 packets and will reach the destination. Right? And then if you want to read it, the same thing will happen again. Did you notice something special on this animation? Yes, some of the packets had different routes. This may and typically happens, for example, on the internet, on the heavily loaded parts of the internet, there are parallel paths. That has lots of benefits. And very often we do equal costs multipath, which means that the data is sent over several paths. So it may happen that all the packets don't follow the same path through the internet. Although in practice today we try to avoid that. We try to make sure that all the packets for a given flow will follow the same path, but there is no guarantee strictly that this will happen. Let's try to have the polling work. Why do you think that the internet is using packet switching rather than store and forward? I don't see that. So if this would be graded, the grading rules are, if you have there is one single correct answer, might not always be the case in the quiz I gave in class. If you have the correct answer, you get +1. If you give an incorrect answer, you get, in this case, -0.5, because there are 2 incorrect answers. So that in average, a robot will get 0. Right. And the don't know gives 0 also. Okay, let's see your solutions if my computer decides to collaborate. So 60%, it reduces buffer required in routers, and that's the correct answer. Here is an illustration of store and forward versus packet switching, right? So store and forward. So this is a time-space diagram. Very useful thing to do when we reason about quantitative things in protocols, delays and throughput. Here, time is flowing vertically and space is horizontal. I'm showing one source, one relay, one destination. If you have a big thing to send and you do store and forward, this is what will happen. You see the thing in between will store it entirely. If you do packet switching and the thing is 1,000 packets, this will be the difference. So the difference is the delay. For the destination here, the delay is twice the time to send the first packet, whereas here it is equal to the time to send the whole thing, plus a little thing, which is the time to repeat one packet. Also, if you look at now the intermediate system here needs to store the entire file. Here it needs to store only a packet. Right? One packet arrives. In this ideal case where the input speed is the same as the output speed, you need to store only one. So this is the major thing. When this was done in the 90s, emails were text. So that was okay. Now that email is photos or other forms of transmission of photos and videos, it would not be doable to have an internet that would store entire videos to download them. So we store only small pieces of a video, and that is why we have packet switching. So the goal of the network is to interconnect everything by using packet switching. Today, we use the network layer called IP, the Internet Protocol. Historically, there were many, many different network layers. Perhaps the most famous ones are AppleTalk and IP. So at the origin, the Macintoshes were interconnected, not using IP. They used their own equivalent of IP, which is a native Apple stuff, which has disappeared. And now IP has replaced everything. But every manufacturer had their own network layer. Microsoft had several even. Now today, they've all been wiped out by two. IPv4 is the first one. And this is an example of a small part of the EPFL network. You see routers. So routers are intermediate systems of the network layer. Those are the systems that receive the packets and send them further, the switching systems, if you think of postcard analogy. And I'm showing a number of computers here. And the main interesting part of this slide is the addresses. So do you see anything specific in those addresses? So those addresses are like the zip code. If you want to send data to this machine, you need to know the address and send it to this address. Now, most of the machines are EPFL machines, and we see that they all have address that starts with 128, 178. There might be also 179 somewhere. So this is a prefix that identifies EPFL in the world. So the second thing to see is that an IPv4 address is encoded in this way, which is called the dotted decimal notation. Dotted because there are dots, and decimal because we write numbers using the decimal notation, which is the normal notation for human beings other than computer scientists. So so here we have numbers that correspond to 8 bits, which means they can be anything between 0 and 255, which is the largest number you can write on 8-bit. 256 minus 1. So it can be anything between 0 and 255, and which is written here.